So welcome to lecture 5. This is about the fundamental theorem. So there are fundamental theorems in a number of areas of mathematics. There's a fundamental theorem of calculus. There's a fundamental theorem of algebra. And being the fundamental theorem doesn't mean to be the most difficult or ultimately most significant theorem in calculus or algebra, but they are just fundamental. So today I'll present the fundamental theorem of tropical algebraic geometry, and I think it's fundamental, but you'll be the judge how important and potentially how difficult this theorem might be. So the setting is we have a field K with evaluation. The ambient setting for classical geometry is the n-dimensional algebraic torus, T to the n, or K star to the n. And this is also in algebraic geometry notation, the spectrum of the Laurent polynomial ring in n variables x1 up to xn. So we're using ideals and polynomials in this Laurent polynomial ring to speak about varieties in T to the n. So let's give ourselves such a polynomial. So if f is a Laurent polynomial in n variables, then we have the tropical variety, which is the tropicalization of the classical hypersurface. And really, this is by definition, this is the same as the hypersurface given by the tropical polynomial. So here, this V refers to the classical hypersurface, and this here is the piecewise-linear combinatorial definition. And one way to say it, it's the set of all W in R to the n such that the minimum in the tropical polynomial, this is the piecewise linear function, when evaluated at W, so this is the minimum of a finite list of linear expressions, if this is attained at least twice. So this is sort of the polyhedral definition here on the right. And we recast this in terms of initial forms. So this is the set of all weight vectors W in R to the n, such that the initial form is not a unit. And this is now over the residue field. We now have the Laurent polynomial ring over the residue field, and the initial form lives there. So if W has coordinates in the value group, then we gave the definition. It can be modified even if some coordinates are not in the residue field. And then there was some fine print about the field having a splitting, which is sort of needed here, although I'll mostly sweep this under the rug today, but to be really precise, we need to distinguish the case where the evaluation has a splitting or not, and if K is an algebraically closed field, then the evaluation always has a splitting. So a simple example, let's say we are in three-dimensional space, and we take the linear polynomial x plus y plus z plus 1. Then the variety of this, well, what is it? Well, it's a plane in three-dimensional space, but the three-dimensional space is a torus, right? So it's really correct way to think about this. This is the projective plane minus 4 lines, right? So really you have to take P2 minus the x-coordinate, the x-axis, the y-axis, and the z-axis, and also the line at infinity. Okay, so this is really the complement of an arrangement of 4 lines in the plane. That's the classical hypersurface defined by this equation f in T3. What is the tropical hypersurface? So the tropicalization of this tropical plane, right? So this open tropical plane, P2 minus the 4 lines, is the set of all W in three-dimensional space such that the minimum Well, it's easy to tropicalize, right? So the tropicalization is the minimum of W1, W2, W3, and 0. And this is attained twice. So this is the definition up here. So there's 6 possible cases, right? I take the minimum of 4 things, and if 2 of them are equal and attain the minimum, and are less or equal to the other 2, that's one cone. That's a 2-dimensional cone in 3-dimensional space. So this is the union of 6 2-dimensional cones in 3-dimensional space. They meet along 4 rays, and of course there's the origin as a 0 cell. So combinatorially, we can describe this as the fan over K4. So K4 is the complete graph on 4 nodes, right? So the complete graph on 4 nodes has 4 vertices and 6 edges. So this fan has 4 rays and 6 2-dimensional cells. So this is the tropical hypersurface. Now, here's the first theorem of the day. So this is an early version of the fundamental theorem. And this was published without proof in a manuscript by Misha Kapranov very early on in the development of tropical geometry. So this is essentially the fundamental theorem in the case of a hypersurface. So let me state this. So let's now assume that K is algebraically closed, and let's assume that the valuation is non-trivial, with non-trivial valuation. So this means there exists some field element, some non-zero field element that has valuation other than 0. So there exists, so valuation is not identically 0, and let's just give ourselves a polynomial, and as above, this is a Laurent polynomial. So we're giving ourselves a Laurent polynomial f. So then the tropical hypersurface the object given in different forms above is equal to the closure equals the closure in n space in R to the n of the following set. So I'm going to give you a subset of R to the n of which the tropical hypersurface is the topological closure in the usual topology on R to the n. And what we do is we take the vectors val y1, val y2 up to val yn. So we take n vectors whose coordinates lie in the value group, and y is any point in the classical variety. And just to make sure, this all takes place in the torus, right? So I take any point in the classical variety. Its coordinate are non-zero elements in the big field. Each of these coordinates has a valuation that's in the value group, so it's in R. And then I take all of these vectors, and then I claim the topological closure of this set is equal to the tropical hypersurface. Now, one inclusion is not difficult to see, right? Namely, the inclusion that this set is contained in the tropical variety. If you have a classical point, and you look at these valuations, and you plug this in to the tropical polynomial, then the minimum must be attained twice. And the reason is that f of y is 0. F is a polynomial. It has a bunch of terms. You plug in y into these terms, right? Y has non-zero coordinates, right? So then, I have 17 terms. Afterwards, I have 17 scalars. But these 17 scalars add up to 0, right? Now, if 17 scalars in K add up to 0, 2 of them, the 2 lowest, have to cancel, right, in the valuation. That's an axiom that follows from the valuation axiom. So the lowest term has to cancel, and therefore the minimum has to be attained at least twice, right? So just by the properties of cancellation coded in the valuation axiom, this set is contained in the tropical hypersurface. Since the tropical hypersurface is closed, the closure is contained. So one inclusion is very easy. So the non-trivial part is the other inclusion, right? So the hard part is if you pick a point W in the tropical hypersurface, I claim there exists a classical point up there that maps to it under the valuation map, right? So the fiber is non-empty. Over every W in the value that has coordinates in the value group, the fiber is non-empty. Well, actually, it's better than that. Not only is the fiber very empty, the fiber is actually really big, right? Let me make this precise. So fibers are actually big. If F is irreducible and W is in the tropical hypersurface, and we need to assume that its coordinates are in the value group, then the fiber is the set of all classical points that attain the prescribed omega for its valuation is really big. It's actually dense. It's Zariski dense in the classical hypersurface. Okay? So the furthermore sentence says not only is the valuation map onto, it's really onto, right? It's really, really onto. It has a very big fiber. Okay? So that's Kapranov's theorem. Let's see this in action in a small example, what this means. So maybe I'd like to say one more time, so some people are watching remotely, so please hold your questions until the end. If you have questions, please, if you're remote, put them in the chat box. If you're here, I'll ask for a question at the end, and I will repeat each question so it's visible on the recording. So here's an example. Let's say we are in 3 space, and we take the point 0, 2, 3, and this is a continuation, I guess, of the previous example. So that's this example, x plus y plus z plus 1. So I'm going to continue this plane with the 4 lines removed. So the point 0, 2, 3 is in there. Let's take the algebraically closed field of Puiseux series. And so here's a picture of the tropical variety. So this picture is a cartoon of the tropical variety. It's a picture of the complete graph K4, and the tropical variety is the fan over this. So W is some point that lies on this 2-dimensional cone in the interior of such a 2-dimensional cone. Why is it in the tropical variety? Well, the minimum of W1, W2, W3, and 0 is attained twice, right? Because W1 is 0. So minimum is attained twice. So now we need to find a classical point. Now we need to solve the equation x plus y plus z plus 1 equals 0. Our task is to solve one linear equation in 3 unknowns, subject to the constraints that x, y, and z have those valuations. That's the task. But there's not just one solution. There are many, 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 many solutions. It's dense. The fiber is Zariski dense in our surface. So I'm going to pick one. So let's pick x to be minus 1, any complex number alpha squared, any complex number beta t cubed, t squared t cubed. So this certainly has valuation 0. Then I take my y to be alpha t squared. So now I need to assume that alpha is a non-zero complex number. So let's say alpha and beta is a non-zero complex number. And beta times z cubed gives me the third coordinate. So the way I've chosen it, x plus y plus z adds up to -1, as it should. And they have the prescribed valuations, 0, 2, and 3. And you can see the fiber is big, right? You can choose alpha and beta anything. You tack on higher terms. So there are lots and lots of solutions. OK. Now, before we come to the general version, let's talk a little bit more about the combinatorial scenario that we have for hypersurfaces. So proposition 3, 1, 6. What can we say about the structure of the tropical hypersurface given by one polynomial in n variables? So tropical hypersurface is the support of a pure gamma val rational polyhedral complex of dimension n minus 1 in Rn. That's the first part. So, well, pure means that all maximal cells, all maximal faces have the same dimension n minus 1. So polyhedral complex is a finite union of convex polyhedra, some bounded, some unbounded, but all the maximal ones with respect to inclusion have the same dimension n minus 1. That's what it means to be pure. A polyhedral complex just says the polyhedra fit together nicely. The intersection of any two is a common face of each. Gamma val rational means that the affine span of every polyhedron here is described by inhomogeneous linear equations, the coefficients of which are real numbers in the value group. So think about gamma val as the rational number, so everything is defined with rational coefficients. Now we can be more precise. We can say exactly what this is, namely, it is the n minus 1 skeleton, of the polyhedral complex that is dual to the regular subdivision of the Newton polytope of f given by the valuations of the coefficients. Okay, so I look at all the monomials in f. I plot the exponent vectors. It gives me a collection of lattice points in n-dimensional space, integral points. Then I assign a weight or height to each such point. I pull that out of the screen dimension. I pull that out of the n-dimensional space towards u into the n plus 1 dimensional space. I take the convex hull. I take the lower faces. That defines a polyhedral subdivision of the Newton polytope, a regular polyhedral subdivision. If the coefficients are general enough with their valuations, this will be a regular triangulation. And then there will be a polyhedral complex dual. So if n is 3, this is dual in the sense of a duality of planar graphs, but it's analogous in higher dimensions. So let's see an example. So it's an example that we've seen, a plane conic, but it's always good to see it one more time. So let's take the rational numbers with the three-adic valuation. Let's make it algebraically closed. So we have the hypothesis of the theorem. Let's take the polynomial 18x squared plus 22xy plus 27y squared plus 29x plus 30y plus 35. Okay, so that's my quadratic polynomial, inhomogeneous in two variables. So I draw the Newton polytope. So I plot the exponent vectors into the plane. The Newton polytope here is the convex hull of these 6 points. So it's the standard triangle inflated by a factor of 2. And then the valuations are 0, 0, 2, 0, 1, and 3. So the 3 is coming from the 27. So this has three-adic valuation 3, and y squared is up here. Here's x squared, and the coefficient of x squared, 18, has valuation 2. So the regular subdivision that's induced by this, so at the bottom you have this triangle that everything is 0, and this guy is at height 1, and this one is very high. So this is the regular triangulation in this case. So now we draw the dual graph, we rotate it by 180 degrees, and then the coordinates of the nodes is where the minimum is attained thrice. And then you take the get the tropical conic. Looks something like this. So first of all, it's always good to identify the coordinates. So these coordinates, I'm going to write them down. 1, -2, 1, -1. Here's the origin, 0, 0. And over here you have -2, 0. Now in justifying this, let me write down the 6 linear functions of which we take the minimum. So I'm going to write these in the respective cells. So u plus v goes here, v plus 1, 2v plus 3, 0, u, 2u plus 2. So these green linear expressions in u and v are the tropicalization of these monomials, right? So for example, so v, let's see. So x squared is here. So I guess this corresponds to 18x squared, and then 27y squared. So that's 3 plus v times 2, and so on, right? So these green expressions. And then the red points are the coordinates where the minimum is attained thrice. Right? So for example, we have u 0, v plus 1, and u plus v. So setting these three things to be equal, u is 1 and v is -1, and that is the red point. So the red point is the unique point where the adjacent green expressions are equal, and the value at which they're equal is less than the value of the three other linear forms at that point. So this is figure, you can see this in figure 313. And once you successfully drawn plane pictures like this, do not rest, but move on to dimension 3. Do never content yourself, we'll take questions at the end, never content yourself with pictures in the plane, because geometry attains structure in dimension 3 and 4. Make sure to draw these pictures in dimension at least 3 and get some sense. Now what does Kapranov's theorem say? Kapranov's theorem says that the fibers are really, really big, that the valuation map is really, really onto, right? So if you have any point over here, so let's say you take this point at 1 minus 3 over 2, this yellow point, there will be xy satisfying the equation f that maps to the yellow point under taking x to its valuation u and y to its valuation v. But not only there's only one such point on our classical conic, there are many, many, many points. There's a Zariski dense in the classical conic. We're now ready to move. Well, not quite, actually. I have a bit more to say about the combinatorics, and then we get to the fundamental theorem at the end. So proposition 3.1.10 is about the constant coefficient situation. So if the coefficients of the given polynomial all have valuation 0, then the hypersurface constructed in this manner will be the support of a fan in Rn, namely, oh, I should have said what skeleton means. So skeleton means the collection of all cells of dimension at most n minus 1. Right? So that's the skeleton. So it's the n minus 1 skeleton of the normal fan of the Newton polytope. So in this case, of constant value, if of trivial valuation, so if all the coefficients of f have valuation 0, then our Newton polytope remains unsubdivided. Then the regular subdivision is just a trivial subdivision. There's only one top cell, and Newton polytope remains unharmed. And then the dual complex described in proposition 316 is simply the normal fan. The collection of inner normal cones, so it's a fan. And the n minus 1 skeleton is the set of all facets of all codimension 1 faces and lower stuff, and that makes the tropical hypersurface. A very good example to think about is the determinant. So 3, 1, 11. So let's say f is the determinant, for example, the 3 by 3 determinant. So in this case, n is 9. So this is a 3 by 3 determinant. It is a cubic polynomial of degree 3, having 6 terms in 9 unknowns. The Newton polytope is the Birkhoff polytope. So the Newton polytope, the Birkhoff polytope, is the convex hull of the 6 permutation matrices, right? So the 6 terms in the determinant become the 6 permutation matrices, 3 by 3 permutation matrices. So we're taking the convex hull of the 6 3 by 3 permutation matrices up in 9-dimensional space. This also is called C46. I'll explain this. And this is related in combinatorics to the assignment problem. So let me draw schematically. Here is a 3 by 3 matrix. Okay, so the Birkhoff polytope, I claim, it lives in 9-dimensional space, but it's a 4-dimensional polytope, right? Now, if you have only 6 vertices, then the convex hull can have dimension at most 5, right? The most it could have is 5 dimensions. But it actually has dimension 4, and the reason is if you add up the 3 even permutation matrices, you get the all-1 matrix. If you add up the 3 odd permutation matrices, you get the all-1 matrix. So therefore, there's one additional affine relation on our 6 points, so the polytope is not 5-dimensional but 4-dimensional. This additional relation, the even stuff and the odd stuff, can be visualized in 4-dimensional space as follows. The 3 even permutations form a triangle. The 3 odd permutations form a triangle. That they sum to the same thing means that the 2 triangles meet in exactly one point in the common interior. So take a triangle, take another triangle, do this in 4 space, make them intersect in exactly one point in the interior. If you take the convex hull, you get the cyclic 4-dimensional polytope on 6 vertices, very basic object in polytope theory. The assignment problem, well, you have 3 workers and 3 jobs, a little company, and you have to assign one job to a worker, and you want to find the cheapest permutation, so there's a cost matrix, and then evaluating the tropical determinant means finding the cheapest assignment. Now, let me refer to a figure that's not in the book, but that's in a different book. NINLA, INLA, is the Invitation to Non-Linear Algebra. That's the book that Mateusz Michalek and I just finished. And then there's a little section, chapter 7 gives you a glimpse of tropical geometry, and a picture of this tropical variety is shown in this diagram. Now, how is this possible, right? We're in 9-dimensional space. This hypersurface has dimension 8. How can we draw an 8-dimensional variety? Actually, it's not so bad, right? And the reason is the low dimensionality of this polytope. So this Birkhoff polytope, which is also the set of all bistochastic matrices, it has 6 vertices, it has 15 edges, it has 18 two-dimensional faces, and it has 9 three-dimensional faces. Okay? So that's the F vector of this 4-dimensional polytope. So therefore, the tropical variety, so the variety, which is a fan, 8-dimensional fan, but it has the F vector 9, 18, 15, right? Now, what does that mean? Well, the polytope is 4-dimensional, right? So, but it's a 9 space. So therefore, the normal fan looks like a book with many leaves, where the spine of the book, the lineality space is the orthogonal complement to the affine span of the polytope. So that's a 5-dimensional space. So there's one lineality space of dimension 5. There are 15 cones of dimension 6. There are 18 cones of dimension 7 and 9 cones of dimension 8. Now, mod out by the lineality space. Do what you are never allowed to do in school. Trample on that book. Cut the spine down until you get nothing. Then we have, you know, a very, very nice fan with 9 rays, 18 two-dimensional cones, and 15 three-dimensional cones. Now, such a three-dimensional cone you can visualize. Intersect this with a big sphere. Now you have a collection of polygons in the plane, right? Now you have a collection of 15 polygons with 18 edges and on 9 vertices, and that is shown in figure 7.1 of Invitation to Nonlinear Algebra. Okay, what is the tropical variety in general? So now, moving away from hypersurfaces and moving away from hypersurfaces and complete intersections. I did mention, did I not, that tropical geometry is the art of going beyond, far beyond Newton polytopes and complete intersections. We are working with arbitrary varieties. So I is any ideal in a Laurent polynomial ring, any ideal, and X is the classical variety, the 0 set in T to the n, its variety. Then the tropical variety by definition is the following set trop X. It's the intersection over all polynomials f in the ideal of the hypersurfaces we discussed during the last 30 minutes, and that's a subset in R to the n. So I take all infinitely many polynomials f in the ideal I carry out this construction infinitely many times, I get subsets of R to the n having these properties, and I intersect them all. That's a subset of R to the n. Now, can you replace this infinite intersection by a finite intersection? The answer is yes. So there is a finite subset, a finite generating set tau of the ideal I will suffice. So this is called a tropical basis. Such a tropical basis exists. In fact, there's an algorithm for computing a tropical basis. Requires some understanding of the Gröbner complex, but using the Gröbner complex you can compute a finite subset tau such that in this intersection it suffices to take f in that finite set. We saw this in Theorem 266. Let me paraphrase this as saying that every tropical variety is a tropical pre-variety. Now, what is a tropical pre-variety? So a tropical pre-variety is a purely combinatorial object. A tropical pre-variety is the set-theoretic intersection of a finite collection of tropical hypersurfaces. So you have a finite list of tropical hypersurfaces, you intersect them, then you get a pre-variety. So for example, an eastern half-ray is a tropical pre-variety. Right? So if you take this line in the plane, and you take that line in the plane, then you see that the set theoretic intersection is the half-ray that starts here. So this half-ray would be a pre-variety. Now this pre-variety is not a variety, right? It's not balanced for one thing. Right? So this is not a tropical variety. It's an intersection of tropical hypersurface, but it's not a tropical variety. In fact, in this case, the only thing the tropical variety can be by stable intersection is the node point here. Okay? And so this would not be, the corresponding polynomials would not be a tropical basis, but you have to throw in another equation that lops off the right stuff on this half-ray. But you can always find a tropical basis. Okay, so here now is the fundamental theorem. Of tropical algebraic geometry. So in the book, this is theorem 323. And it's the generalization of Kapranov's theorem to varieties of arbitrary dimension and codimension. So let's say K is an algebraically closed field, same hypothesis with non-trivial valuation. I is any ideal in the Laurent polynomial ring over that field. X is the classical variety in the n-dimensional torus. Then the following three subsets agree of R to the n. Following three subsets of R to the n coincide. So 1 is the tropicalization of X according to this definition. So it's the intersection of a collection of tropical hypersurfaces, and if you have access to a tropical basis, then you only need to intersect the tropical hypersurfaces coming from that tropical basis. You only have to carry out the combinatorial description construction finitely many times. 2, the set of all W in R to the n such that the initial ideal is actually not the whole ring, right? And here we're using the fact that there's a splitting to the valuation. So this is the set of all W, so that the initial ideal in the raw polynomial ring is not the whole ring. And back in the polynomial ring, often you're working in the polynomial ring, and this is equivalent to saying that the initial ideal contains no monomial. It's the set of all W such that the initial ideal is monomial free. And finally, 3, the closure, topological closure, and this is the main point of the valuation applied coordinate-wise to the classical variety. So it's val y vectors in R to the n for every point y upstairs in the classical variety. So I take any point y in the classical variety. I take for each coordinate the valuation. That gives me n numbers in the value group. And this lands that set is val x. And the topological closure of this is x, is the topicalization of x. Now, one word about the topological closure. It's in some sense a shortcut. It's in some sense an artifact of the way we choose the field and the valuation, right? So last time somebody asks, what kind of values fields are there? You can fix this. You can get rid of the closure by choosing a large enough field. So if you choose a field whose value group is R, so if you have a version of Puiseux series where the exponents are real numbers, then you can delete the closure here. And this is always possible. As I told you, model theorists, they know a lot of valued fields, right? So if you don't like the closure, you can make the field bigger, and you don't need it. But this theorem is not just true, it's very true, right? So if x is irreducible, so fibers are big. If x is irreducible, and W is in the tropical variety and has all coordinates in the value group, then the fiber set of all y in x such that the valuation of y is the given point W is the risky dense in upstairs in the variety. Okay? This is a very strong claim. This says not only is the map is onto, but the fibers are very big. Now, having this statement is very useful, having this big fiber statement, because you can carry it along in the induction. So in the proof, I'll say a few words about the proof. The proof uses various forms of induction, and sometimes you can prove a stronger theorem, but if you state a stronger theorem, it actually makes the proof easier, right? Because you can work your way up in the induction, and that is exactly what happens here. Okay? So the proof structure is as follows. So the easy parts, first of all, 3 is contained in 1. Well, that's the same thing I said so far. So suppose you have any classical point in x, y, and you look at its valuation, W, right? So then I have to argue that this W is in trop x. So that's to say, for any polynomial f in the ideal, W has to be on that tropical hypersurface. Right? So for that f, minimum has to be attained twice at W, and that is because f vanishes classically at y. Right? So f is a polynomial, it vanishes at y, so therefore the lowest terms have to cancel. Right? F of y is equal 0, that's an identity. The lowest terms cancel, so this is cancellation of lowest terms. Now also 1 contained in 2 is not too bad, right? So, well, the tropical variety of x, so something is there, so for every, so it's easier maybe, let's think about the contrapositive. So I say that the complement of 2, not 2, so it's contained in the complement of 1, so the complement of 2 is all weight vectors such that they are the whole ring. Right? So it's a W, set of all W, such that some polynomial f in the ideal has a leading monomial. So there's this nasty polynomial that has a unique leading term. Right? If that is so, then the minimum is not attained twice here. Right? So it's quite easy to see that the complement here is contained the complement there. So the hard part is 2 is contained in 3. Okay, so this is where all the work is. Now, of course, in these lectures, I sweep all the hard parts under the rug, right? I do the song and dance. I'll tell you how nice tropical geometry is. But the proofs are not so easy, right? So that's why if you really want to get into this, you must actually study the proofs. So let me say a few words about the proofs. So of 2 is contained in 3. So what are some of the ingredients? Well, first of all, you will homogenize. You homogenize the algebra and use the corresponding homogeneous ideal that describes the projective closure. So this is in K x0, x1 up to xn. And the reason we've seen in section 2.4 to have a nice Grobner theory, to have all the flatness you want, to have a nice Grobner complex that covers all of R to the n, which is R to the n plus 1, mod R1. So to have a nice Grobner complex that covers everything, it is convenient to work with homogeneous ideals. So we will work with homogeneous ideals. So now, after this convention, X is replaced, which was a very affine variety. So earlier here we had a very affine variety in a torus. Now we're looking at its closure in projective space. So now X is a projective variety. And, well, the tropicalization of X naturally lives in what used to be called tropical projective space, lives in Rn plus 1 mod the all-1 vector, right? Because if I have homogeneous coordinates, homogeneous polynomials, then the all-1 vector never breaks ties. It lies in the linearity space of everything in sight. So therefore, we can regard our variety in an n space. I said this used to be called the projective space. It's no longer. Sometimes people call this now the tropical projective torus. The disadvantage of this is that it's not compact, right? So geometers really want their projective space compact. And this has been resolved in the meantime, and that's happening on chapter 6. So Friday in a week, we'll actually talk about tropical projective space. Here it looks like projective space, right? Because projective space is really affine space modulo scaling, which is, modulo tropical scalar multiplication, which is tropical scalar addition, and that's where our projective variety lives. Now its support, by construction, well, I'm sorry, its refers to this, the tropical variety, its support, it is the support, it is the support of a subcomplex of the Grobner complex of this homogeneous ideal. Well, that's because the property for an initial ideal to contain a monomial or not depends only on what the initial ideal is, right? So the Grobner complex is a stratification of W space such that the initial ideal is constant on each stratum. That was the definition of Grobner complex. Remember, the initial ideals are defined over the small field, over the residue field. Okay? So you just go over the Grobner complex, and of course, once a cell is in, then every face of it is in also, right? So once you have an initial ideal that's monomial free, then every smaller cell, that means things of which it is the initial ideal, is also monomial free. That's all part of 2.5. So this is the Grobner complex. Now, I urge you to draw some Grobner complexes. Do not do it in the plane, okay? Do it in 3 space. Do not just do one equation. Take two linear equations. Give yourself a system of two linear equations and three unknowns. X plus y plus z plus 1. X plus 2y plus 3z plus 17. Okay? Contemplate the variety. That's a line in 3 space. A line with 4 points removed. That is to say, a punctured Riemann sphere with 4 punctures, right? It's a line. But try to visualize the Gröbner complex. Compute all initial ideals. And I think this is a very good exercise. Yeah? So solve a system of two linear equations in 3 unknowns in the sense that you find its tropical solution set by inspecting all cells in the Gröbner complex. Now finally, you do not just need polyhedral combinatorics in the proof. You also need quite a bit of a dose of commutative algebra. So let me write this big. You do need commutative algebra. And you need the commutative algebra to talk about the initial ideal. So now this is the initial ideal of 0, w of the homogeneous ideal. Where does the 0 come from? Well, we homogenized, right? Remember, we took our very affine variety in n space, the n-dimensional torus. We constructed the projective closure. So now we have an ideal in n plus 1 unknowns. And 0 is the homogenizing coordinate, right? That's the multiplicatively neutral element. We tag this on the first coordinate. So this is the homogeneous initial ideal. And you have to apply some commutative algebra. And bearing in mind, this is now defined over the residue field in the homogeneous ideal here, right? So you need to study this ideal. You need to study the variety, the primary decomposition. And we'll get back more into this in the next lecture. Okay, so again, here is the fundamental theorem. The fundamental theorem says that every tropical variety has 2 equivalent descriptions. One is an equational description. It says the tropical variety has a construction by equations, by a finite list of tropical polynomials, and you construct these complexes and you intersect them. Right? That's sort of a combinatorial polyhedral construction. But for an algebraic geometer, it is more natural to use this description. You just take the classical variety upstairs, and you just map in under the valuation map, under the coordinate-wise valuation map. And these are equivalent. Having this equivalent and having both of these characterizations at your disposal makes this a very powerful theorem, right? A very powerful theory. So this characterization from the classical variety is very useful for proving things. It's very bad for computing things. This Gröbnerian description in 1 and 2 is very good for computing things, but it's pretty bad for proving things. But having both, you can not just prove, but you can also compute. And not just compute, you can also prove. Thanks for your attention. It's time for questions, and including questions possibly in the chat box. So the question is, can you go over the inclusion of 3 in 1? So 3 is the closure. Oh, this is a typo. Right? That's just val. So 3 is all the vectors w that I get by applying the valuation to a classical point in the variety. And 1 is the tropical intersection of tropical hypersurfaces. Okay? So let's say I have such a w. So it comes from a classical point y. Okay? So I need to show you. So I need to show that the valuation of this classical point is inside the tropicalization of x. Now what does that mean? To show this, I need to show it's in the tropicalization of every hypersurface for all f in my ideal. Okay? So you have a point on the variety and you have a polynomial that vanishes on it. Okay? Now let's visualize what this means. F is a polynomial. It's actually a Laurent polynomial. It has a bunch of terms. Something y to the something plus something y to the something, right? And that's 0. So it's a sum of non-zero things in the field that adds up to 0. Now, these summands are non-zero field elements, so they have valuations, like 3, 5, 11, something, right? But the term of lowest valuation must cancel another term. That was the very first corollary of the definition of valuation. Think about power series, right? If you have a bunch of power series in one variable that add up to 0, right? And the lowest term that you see must occur at least twice, right? If the lowest term occurs only once, then it can't cancel. That's what I'm saying. That's the inclusion of 3 in 1. Yeah, you really have to construct the point in X. So you have to have the lifting. So one of the ingredients is a proof in the zero-dimensional case. So you try to reduce yourself to the zero-dimensional case. So let's just think X is a classical zero-dimensional variety. Okay? Well, first of all, you need to prove, so it's a finite set of points. Right? So I claim that in this case, trop X is also a finite set of points. Not entirely obvious, right? Because you have this zero-dimensional ideal, right? And trop I is combinatorially defined, but it's not clear that there's a finite, and it's sort of not obvious if you think about like set theoretically, right? So you think about, well, now it's gone. If you think about intersection of the two lines in 3 space, it's not obvious. So that's one ingredient. But you need some commutative algebra. You need to look at this ideal, look at its Gröbner basis, apply the shape lemma from Gröbner basis theory for zero-dimensional ideals, and then you see that the tropical variety is actually finite as well. Okay? Well, you're not done, right? Because now you have to take every point in the tropical variety and build the classical point. And you do it. Right? So this is a kind of Hensel lifting type argument. Right? So okay, so now you have the zero-dimensional case. So now you have a higher-dimensional variety. And now you do some kind of intersection with appropriate hypersurfaces. And then in the meantime, you always carry along this stronger conclusion that the fibers are Zariski dense. That actually helps you. You're proving a stronger statement, but it helps you in the induction. Yes, so the question was, why do we need the hypothesis that the valuation is non-trivial? Well, if the valuation were trivial, right? So if we had, for example, the complex numbers here, right? Then it's very false. Then the statement is very false, right? So there's a tropical variety. It's a perfectly good, polyhedral fan. It's a bit like some kind of tropical line, maybe something like this. But of course, this set is just a set 0, 0, just a point, right? Because val y has coordinates in the value group. The value group is just 0. So this set is only, if the valuation is trivial, it's simply the point 0, 0. Okay? So if the valuation is trivial, such as over the complex numbers, then it's very false. Then this is just one point, and this can be anything, can be arbitrary high dimension. So as soon as the valuation is non-trivial, the value group is actually dense. Right? So as soon as you have some element of valuation 17, you also have, elements of valuation minus 17 and 17 over 8, and you get a big Zariski, you get a dense subgroup, and that makes enough points to make this true. So this lifting is implemented. So in singular, for example, soon to be cocoa, in singular you have a command that you can specify a W, and it will make a point. It'll give you the first couple terms, of the Puiseux series and each coordinate. Oh, I see. That's a very good question. So I stated that the fibers are Zariski dense, the fibers on the tropicalization. What about the complement? Is this somehow given algebraic? Is this somehow given by algebraic equation? And the answer is no. So it is given by equations, but you really need to go to an analytic setting. So this is called rigid analysis. So there is something called the Tate algebra. So there is some interesting, sort of analytic situation, but you need kind of analytic equations to cut out these fibers. So they're definitely not algebraic. Complement is not algebraic. Okay. So the question is, what if we replace the definition of tropical variety by intersection by stable intersection? Would it then work? No. Suppose you have a hypersurface just by one equation. So then even by stable, oh, I see. Then you would stably intersect, I see. I think the answer is no, but I need to think about it a little bit more, right? So, because stable intersection only makes sense for sort of complete intersections. So, for example, you typically have variety, let's say about determinantal variety that require many, many more equations than the ambient dimension. I think you can write down a counterexample in every sense. So, yeah. Good question. Okay, so why don't we take a 5-minute break and then we'll continue with the structure theorem.